This set of notes is about acid-base basics. As usual, you'll be able to find a set of notes provided for you in Schoology. Add summary and question at the end. You know the drill. If we go way back in time to where acids first and base chemistry first started, the first definitions that we have for what's an acid and what's a base came from Arrhenius, also the same guy that did the Arrhenius equation, which really has nothing to do with this, but this was some of his other work. And that's that an Arrhenius acid is a substance that forms hydrogen ions when it dissolves, okay, or when it dissociates. And so some terms that go along with acids that we oftentimes use are monoprotic. Okay, so mono, of course, one, protic means proton. So this gives us one hydrogen plus ion because a hydrogen plus ion is just a proton. Diprotic, of course, gives us two hydrogens. Triprotic gives us three hydrogens. And then polyprotic would be anything that's di or triprotic. If we think about our strong acids that you guys have been memorizing, and we think about one like hydrochloric acid, this is monoprotic because when it dissociates, it's going to turn into hydrogen ions plus chlorine ions, and so we get one hydrogen ion out of that. If we have something like a strong acid like sulfuric acid, when that dissociates fully, it will end up giving us two H plus ions plus an SO4, two minus ions. So this, of course, would be diprotic. Okay. By Arrhenius's definition, a base is a substance that forms OH ions when it dissociates. All right. So that, again, all of our strong acids would, of course, do that, like lithium hydroxide, or calcium hydroxide. Okay, so again, those are the definitions for that. The Arrhenius definition, however, is kind of limited because it only works when we're talking about things that are aqueous solutions. And so as time went on, they discovered, hey, there's things that act chemically like acids and bases but aren't aqueous solutions. So we need a better or stronger definition than that. Which brings us to Bronsted-Lowry definition of acids and bases, which is the predominant definition that we use when we are dealing with things in AP chemistry. And basically what Bronsted-Lowry says is that an acid is any substance that donates protons. It's a proton donor, H+, right? And so again, if we're monoprotic, it's going to donate one hydrogen ion. If it's di, it can donate two, tri, three. Polyprotic, again, anything that can donate more than one hydrogen ion. Bronsted-Lowry bases become a substance that accept protons. In other words, they are proton acceptors. And that's what goes on with that. And this is more powerful because this will work not only with aqueous solutions, but it also works with gases. All right, so we've got our solution chemistry and our gas chemistry covered by the Bronsted-Lowry definition. Other definitions that we use, we talked about these ones yesterday, right? A strong acid or base is going to dissociate completely or nearly completely into ions. So if we take any one of our strong acids like HCl, this is going to turn into all hydronium ions plus all chloride ions, and we'll come back to that and what we mean by hydronium in a minute. But basically, it's going to turn all into hydrogen plus chlorine. It's going to be a full dissociation. A weak acid or base is going to be one that does not dissociate completely. It remains primarily molecular, but we do get a little bit of hydrogen or a little bit of hydroxide off of it, or a little bit of hydrogen accepted or a little bit of hydrogen donated. So if we think about this, this is acetic acid, HAC. And when this dissociates, you get mostly acetic acid molecules. So you still have mostly HAC. But you do get a little bit of hydrogen ion and a little bit of acetate ion. All right. So strong and weak acid or bases, this definition is all about dissociation. Okay. And so what we need to make sure is that we are not confusing that process of dissociation in strong and weak with what we mean with concentration. Okay. So a strong or weak acid means percent dissociation. Okay. If it's not strong or weak solubility, so in other words, not how much is going to dissolve, and not strong or weak reactivity, in other words, how strongly it reacts, right? So if we think about concentration, for example, we can have a concentrated solution of a strong acid or a concentrated solution of a weak acid. What do those mean? Well, the concentrated just means that we have a lot of the chemical in the solution, right? Strong acid means we have high dissociation. Weak acid means we have low dissociation. Okay, so both of these species up here have a lot of acid in them. These ones over here are more dissociated. Those ones over there are less dissociated. So they're both concentrated solutions, but one is strong and one is weak. So what I need you to do for me here, in addition to knowing things, is one thing I need you to do is I need you to know the strong acids and strong bases, all right? Because everything else is weak. So strong acids are HCl, HBr, HI, HClO3, HClO4, HNO3, H2SO4, and HiO4. There are some mnemonics that exist out there in the world. I don't love any of them, but you might find some that you like. But if you did a mnemonic device for the strong acids, you should be able to figure out, find one for those 8 to help you remember them. The strong bases all have hydroxide in them. Okay, so anything that's in group 1, the alkali metals, any hydroxides of those, like sodium hydroxide, would be a strong base. The other ones that are strong bases are anything from group 2 hydroxides, but those are anything with calcium or heavier, in other words, calcium or lower down on the periodic table. That would be an example of a strong base. Okay, so strong acids, strong bases, you need to know what those are. All right, so now that we've discussed the basics of what an acid and a base are and some definitions for those and definitions between weak and strong acids and concentrated and dilute acids and bases, we can go ahead and we can talk about some basic acid-base reaction. Okay, this is called a neutralization because we go from, if we put the acid and the base together in the proper combination, we end up with a neutral solution. All right, so in a very simple neutralization reaction, you start with 2 aqueous reactants, and it's a double replacement. One of your reactants is an acid, the other one is a base. The products that you get out are water and some kind of ionic compound. That ionic compound can be soluble or insoluble, so it's the formation of water that actually drives this equation to happen in terms of net ionics. All right, so if this is our equation here, HCl plus NaOH goes to H2O plus NaCl. So strong acid, strong base, we're putting these things together. It's a double replacement, so the hydrogen and the sodium are going to swap spots. And then on the other side, what we end up with is then HOH, or water, and NaCl, which is our aqueous salt. Okay, so we always end up with an acid and base going in, salt and water coming out. That's our basic neutralization reaction. Now we said the formation of water is what drives a neutralization reaction. However, there are some other things that can cause a double replacement or replacement reaction to happen that we kind of need to be aware of in terms of reactions going on. So one thing that drives us is if you have a molecular compound that has a low solubility in water, in other words, an insoluble compound, you can end up getting stuff coming out of solution. One way of doing that is producing gases. Gases are typically not very soluble in water, and so you get bubbles being formed. So an example of this would be hydrochloric acid and sodium sulfide. Again, double replacement reaction. And so you end up with hydrogen sulfide gas, which bubbles away, as well as our sodium chloride in solution. The formation of this drives the reaction to a more ordered state. And so in other words, you can get that gas being formed. Another thing that can happen to do this is if you get unstable products that decompose. So sometimes when you do the double replacement, you end up with something on the other end which is easily decomposable. So for example, hydrochloric acid and sodium bicarbonate. Okay, if you do that and do the double replacement, you get sodium chloride and carbonic acid. Now carbonic acid is super unstable in aqueous conditions, and so as a result of that, it automatically breaks down into water and carbon dioxide. Okay. Turns out there's a whole bunch of these like this, right? So gas formation, what we got to look at is one way that molecular compounds, or one way of things that don't just form precipitates, where the gas is actually what drives it. The formation of hydrogen sulfide gas as well as hydrogen cyanide gas. Both of those two are gases that can drive a reaction to actually happen with a double replacement. Unstable products that decompose. If we get a product that is carbonic acid, sulfurous acid, nitrous acid, any of those three things will actually break down further. Carbonic acid turns into water and carbon dioxide. Sulfurous acid turns into sulfur dioxide and water. And nitrous acid turns into nitrogen dioxide, nitrogen monoxide, and water. And the last one, if we have ammonia, ammonia NH4OH, ammonium hydroxide, this will form ammonia gas and water. Okay, if there are two of these that I would suggest that you actually pay some attention to and make sure you maybe try to commit to your memory, is that first one there, the carbonic acid reaction, and this bottom one here, the ammonium hydroxide reaction, because those two are both reactions that very frequently we see in chemistry. All right, so when we have neutralization, then we can go ahead and we can have titration. We can do titrations, and we can do some stoichiometry that helps us figure out knowns and unknowns again, just like we did with redox, but this one is with acids and bases. All right, so here's an example of this. 47.5 milliliters of 0.5 molar H2SO4 is required to neutralize 20 milliliters of NaOH. What is the concentration of the NaOH? All right, so first thing is we're going to write the chemical equation. So we got H2SO4 plus NaOH. On the other side of that reaction, we are going to have, it's a double replacement, so we're going to end up with water plus NaSO4, and of course that's going to be Na2SO4. Balancing the reaction then, we put a 2 there and a 2 there, and we're all good. Okay, so now we do the stoichiometry with this. Okay, so first thing we need to do is start with the amount of the known. So 45.7 milliliters of known. Okay, and then we're going to go ahead and we are going to take that and turn that into a number of moles of our known. So we know that this is 0.500 moles of H2SO4 per 1,000 milliliters, or 1 liter of H2SO4. That cancels out. Now we're at moles of that. Next thing is our stoich. So from our equation up there, 1 mole H2SO4. And we're trying to figure out how many moles of NaOH does that correspond to. So 2 moles NaOH. Moles of H2SO4 cancel. Then we're going to go ahead and take that moles of NaOH and turn it into a molarity. So in order to do that, we need to be moles per liter. So I'm just going to go 1 over 20 milliliters. And we can go 1,000 milliliters per liter. And that will cancel that out. Okay. If we go ahead and we do that entire calculation, then we can get the molarity of the NaOH solution. And if we do that on our handy dandy calculator, we get 2.28 molar. All right, all of the neutralization reactions that we've discussed so far have been reactions where we assume that we have a strong acid and a strong base, and so the neutralization is complete, or it's a complete reaction. But that doesn't always happen. Sometimes it does, sometimes it doesn't. But oftentimes we end up with equilibrium situations. So it's oftentimes to think of acid-base reactions as proton transfer reactions. All right, so here's the reaction between hydrochloric acid and water, okay, which is just the simple dissolution of this particular substance. And if we think about that, here are our Lewis diagrams for that. And what happens in this process is you'll notice that right here we get a hydrogen being transferred from this chlorine over to this water molecule over here. So we would say that this then is our hydrogen donor, proton donor. So there's our acid. This is our proton acceptor, and that's our base. Okay, and so you end up then on the other side with chlorine ions and this ion right here, H3O+. which is what happens when you get hydrogen into water, and it's called the hydronium ion. All right, so now in that previous example, we had full dissociation, so that was a reaction that goes to completion. What happens if we've got a reaction that doesn't? In other words, we have weak acids and weak bases and things like that. Well, in these particular cases, we can go ahead and write out an equation, and we start labeling and using terminology of acid and its conjugate base, base and its conjugate acid. All right, so the one here on the product reactant side, just by convention, we don't use the term conjugate. On the product side, we do use the term conjugate, and that's just by convention. All right, so we think about this in this particular reaction. We'll see what are the two species that are related from left to right. Well, HNO2 and NO2 are obviously related to one another. And in addition to that, we have our H2O and our H3O plus, which are obviously related to one another, right? Those species are super similar. And so then we think about what happened. Well, over here, we went from HNO2 over to NO2 minus. So what happened? Well, this donated or lost a hydrogen or donated a hydrogen. And so as a result of that, we refer to this as our acid. And over here, the opposite of that then becomes its conjugate base. And we'll talk about why that is in just a second. What happened to this base here of H2O? Well, it became H3O plus. And so that means it must have accepted a proton. And so it's a proton acceptor. It becomes a base. Now, since this is an equilibrium expression, we can go both ways. So if I likewise come over here to our H3O plus and I take a look at that, if this reaction is going in reverse, we go from H3O plus to H2O, which means that this lost or donated a proton, and so it becomes known as our conjugate acid. Same thing, we said the opposite of the acid was the conjugate base. Right here, our base. If we run this reaction in reverse, we add a proton, or in other words, this thing is a proton acceptor, and so it becomes a base. It is our conjugate base. All right, so you can always look at this and understand that when you're labeling things, you'll have the acid and the base on one side, the conjugates on the other, and then you just got to figure out what's related to what and what's adding protons and what's losing protons to assign what is the acid and the base. All right, so then we can always think about in terms of in any pairs of acids, bases, and their conjugates, we can always figure out in those pairs what are the strong ones and what are the weaker ones in each particular case. And it turns out that if I have a strong acid, any of those ones that we learned, the conjugate of those is going to be something where the basicity of it is negligible. Okay, so a strong acid will give us a negligible base atom on the other side. And the reason for that, again, is these completely dissociate. So like in the case of HCl, if I go to H plus Cl minus, okay, this reaction is not going to go in the reverse, right? This reaction is not going to go in the reverse, right? It's got a strong equilibrium to the right. It's complete dissociation. And so as a result of that, this is not a very basic substance at all because it cannot regain that proton back onto it. It's not going to go back to the way that it was. Okay, same thing with strong bases. The conjugates of them are going to be acids of negligible acidity or a species of negligible acidity. So for example, CH3 goes to CH4. Again, it's going to be strong bases going in that particular direction. You'll notice the positions of water and hydroxide here, right? And up here, you'll notice the positions of hydrogen and water up there in terms of being acids and bases. One thing you might notice is, oh, look, water can both be an acid and a base. A fairly strong one of each, actually, or a fairly weak one of each, actually. But nonetheless, it is there. In the middle here, what you will find out is that the stronger the acid that you have, the weaker its conjugate base. And the weaker an acid we have, the stronger its conjugate base will be. So a few different things to be thinking about there. All right, so thinking about this even more was in terms of when we actually see it in a reaction. We're going to look at this one first of all. We have HCl plus water goes to H3O plus Cl minus. We've used this example a few times. And we're going to go ahead and we're going to label the acid-base pairs. Well, HCl we know is an acid, right? And so along the way, if it's an acid, that means it's a proton donor, so it's going to lose its hydrogen. And after we lose that hydrogen, what are we left with? We're left with just the Cl minus ion. So this is going to be the conjugate base of that substance. Okay, likewise, over here, we're going to have our water, and we'll see what happens to water along the way. The water actually picks up that hydrogen. So in other words, on this side, it's a hydrogen or a proton acceptor. So this is our base. And over here, this is going to be our conjugate acid. Okay, so we go ahead and put those things in there. Right? And so it says, which base is weaker? We can figure this out by looking at, in this particular case, do we know anything about the acids and bases that we have? Well, of course we do. We know that HCl is a strong acid. And we know from what we learned in the previous slide that the strong acids have weak or negligible conjugate bases. Okay, so that means that Cl minus has to be a very, very weak base. H2O and H3O, neither of those are strong acids or bases. We know that. And so this must be a weak base. And the conjugate of a weak base is a weak acid. Which of those two is stronger? We don't know unless we actually go and look at a table or think about it a little bit. All right, so which base is the weaker base? There's our weaker base, right? And this says this is the side that equilibrium will favor. Okay, well, that makes sense because we know that this is a complete dissociation, so we know that equilibrium is way far over there to the right. And so that makes sense with that ago. Okay, so in general, whenever we talk about things, equilibrium is going to favor proton transfer from the stronger acid to the stronger base. Okay, and so that's going to be on one side. So in this particular case, we have stronger acid. There's our base. So we do know that this is the stronger base of the two. This is the stronger acid of the two. All right, so just to summarize that, because HCl is such a strong acid, the K has got to be incredibly large, so we don't even consider this an equilibrium. It is product favored for sure.